Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to continue with Lagrange's equation of motion. This is the overview of what we are going to discuss today. First, we are going to look at an example of continue with the Lagrange's equation of motion and discuss an example. Then we are going to look at Hamilton-Ostogradsky principle. This is an extension of Hamilton's principle, where we also consider externally applied forces or non-conservative forces, for which we do not have a potential. We will continue first with an example of Lagrange's equation of motion, how to derive it for a little more complex system like this vehicle with ground excitation. We have a vehicle body which is connected to by these compliant connections, which are drawn as springs and mounted on, let us say these are some actuators which can give some ground excitation. It could be wheels as well. The generalized coordinate for this system can be taken as x g, this g is the center of mass of this automobile, x g, y g, z g, and psi theta phi. Therefore, we have the coordinates of the center of mass and the orientation in terms of yaw, pitch and roll. You will notice that I have a coordinate system which is fixed at g, x, y, z, and we are going to express the orientation in this body fixed frame, so as to make the moment of inertia tensor a constant. Now, Lagrange's equation of motion has this standard structure, as we have seen, d dt of del L del q I dot minus del L del q I is equals to 0, where I goes from 1 to 6, and what are these coordinates? They are the generalized coordinates x g, y g, z g, psi, theta and phi. Therefore, we will have 6 equations of motion. Now, for the orientation part, we recall what we have discussed in our previous lecture, where we derived the rotation matrix, the orientation of a frame given a yaw, pitch and roll. The basic fundamental rotation matrices about the individual axis are yaw about z by an angle psi, z naught by an angle psi, pitch by an angle theta about the new y axis, which is y 1, and the roll phi, roll angle is phi, about x 2, which is the new x axis, and the fundamental rotation matrices were all written. And we had finally written out this rotation matrix from frame 3, which is fixed to the body, to frame 0, which is the inertial frame. Therefore, this rotation matrix completely specifies the orientation of the body of the vehicle, or that frame x, y, z, which is fixed at the center of mass. Also, recall this angular velocity written in the body frame, angular velocity in terms of yaw rate, pitch rate and roll rate. Omega 3 is the angular velocity vector as represented in the body fixed frame x, y, z. Psi dot is the yaw rate, which is about z 0 expressed in frame 3. Pitch is theta dot, pitch rate is theta dot expressed about y 1 in the body fixed frame 3, and roll is phi dot about x 2 in the body fixed frame, and these were the vector representations of these axes. And finally, we had this transformation from the yaw rate, pitch rate, roll rate to the angular velocity vector in the body fixed frame. Once these things are done, we are now ready to write down the elements that are required for our Lagrangian. First is the kinetic energy of the system. I am considering that the kinetic energy contribution comes from the vehicle body. This has two parts, the translational kinetic energy, which is written here, half times mass times the velocity square of the center of mass. The rotational kinetic energy, this we have seen, is half omega dot I g times omega. I g is the moment of inertia tensor about the center of mass, which I consider that it is known. If x y z is a principal coordinate system, then I have a very simple form of moment of inertia tensor, which is completely diagonal, but it need not be. And omega is parameterized by the yaw, pitch, roll coordinates, as we have just now discussed, and that too in the body fixed frame. Therefore, using these expressions, I can write down. Now, this is quite complex, therefore, I have not written it here, but we can write this expression of the rotational kinetic energy. Therefore, we have the total kinetic energy, translation plus rotation. Now, we are going to write down the potential energy contribution. Look at the front wheel, this one. You will notice that we have a ground excitation, which is given by R A prime expressed in O, in frame O, and frame O is this. Therefore, we have the ground excitation expressed in the inertial frame, which is fixed to the ground, and we are going to write down first the position of this point, A. How do I write the position vector of point A in frame 0 or frame O? This is position of the center of mass, position vector of the center of mass in frame 0, plus the rotation matrix from 3 to 0 times the vector G A. This is the vector G A from G to A. If I transform it, this is expressed in the third frame, G A is expressed in the third frame as shown here. That can be transformed to the 0th frame or the ground fixed frame by using this rotation matrix. Therefore, I can obtain the position vector R A 0. It is this vector up to G plus this vector, everything written in the 0th frame. Now, if that is done, it similarly follows for position vector of point B. This is point B, and we can write the position vector of point B in the ground fixed frame as position vector of G plus transformation of G B, which can be expressed easily in the third frame, body fixed frame, and I can transform it using the rotation matrix. And similarly for the rear two wheels, the structure remains the same. Then we can write down the position the potential energy of the system. Now, potential energy contribution comes from the springs, suspension springs, and the gravitational potential energy of the vehicle body. Now, here I have written out this potential energy expression is half. This is the difference between R A and R A prime. Therefore, these two vectors R A, this is R A and R A prime is this vector. Therefore, this is the difference vector, this is the difference vector, and we write this difference vector transpose stiffness matrix. In general, I have drawn it like a spring. It appears that it is one dimensional, but it need not be one dimensional. In that case, the stiffness would be a matrix. You can have stiffnesses in various directions. Therefore, this stiffness will have many components, because it will store potential energy if there is vertical displacement as well as there is horizontal displacement, then also you have the spring force, you can have in general. Therefore, this becomes a matrix, and in very simple situations this will be a diagonal matrix. In other words, you will have forces also in the horizontal direction because of displacement of point A horizontally above A prime. Similarly, for the wheel point B, you have the difference again C and D. These are the potential energy contributions because of the stiffnesses. And then we have this gravitational potential energy because of the vehicle body mg zg. Finally, we have the Lagrangian as kinetic minus potential energy. You will have to write everything here. For example, these will involve the roll rate, yaw rate, pitch rate, etc., all those things. These will also involve those angles, because remember we are using the rotation matrix which has this roll angle, pitch angle and yaw angle. Therefore, this is going to be a very complex Lagrangian structure, but once it is written out, the steps are algorithmic. We have a Lagrangian which is a function of x g, y g, z g, psi, theta, phi, and the rates of all these things, and time. How does time enter? Because recall that these are actuators which will give displacements as a function of time. Therefore, we will have time in these elements. It could be a harmonically varying or different kinds of inputs you can think of, which are purely functions of time, which are provided, which are given to the system. So, these are displacements which are given at the base. So, these are time varying functions which will need to be provided. And this will lead us to highly complex coupled second order ordinary differential equations, which will be nonlinear and extremely difficult to solve analytically. Therefore, you have to take recourse to numerical methods for solution. Because of the complexity, we will not discuss this any further, but I hope you understand the way to derive the equation of motion and to solve them. Let us now look back and compare the Lagrangian approach that we have been discussing under analytical mechanics or analytical dynamics, and the way we had used Newton's second law to study dynamics. The first point that comes to mind should be that Newton's law is a local statement. It is a statement about balance of inertia forces and applied forces. or external forces. So, in Newton's second law, when we apply Newton's second law for a particle, for example, we have the inertia force in terms of mass times acceleration, and that is equated to the applied force. Now, this is a local, at every point this is true, at every point. So, that is why I call it a local statement. In the Newtonian approach, what we do? We first fix up the coordinates, of course, but then we have to draw the free body diagram, we have to draw internal forces. When we draw free body diagram, we have to draw these internal forces, which are solved in the process. In the process of solving the dynamical problem, we also get the solution of the internal forces. Therefore, internal forces are part of the solution. Every time we discussed number of equations and number of unknowns. These unknowns had not only accelerations or their integrals, but also the forces, the internal forces. So, that was Newtonian approach. When we start using when we discussed analytical mechanics or analytical dynamics, we started with Hamilton's principle. This statement of Hamilton's principle says that something is minimized over the whole path of the system, or the whole time of travel of the system, or the time over which I am observing the system. Therefore, this Hamilton's principle is some kind of an extremization for some quantity which is global, which is defined over the whole path that we are interested in or looking at. So, extremization of action over a path, this is a fundamental difference. Now, the Lagrange's equation that we derive out of Hamilton's principle, that turns out to be a local statement. So, that is a differential equation, and it is very similar, and we will discuss this further. It is a local statement. What we obtain is a local statement, but which has global implication because we started from Hamilton's principle. In other words, these equations of motion, though they are local statements, but they have global implication. There is something to be minimized or maximized, extremized over the path of motion. Of course, that exists in Newtonian approach also, but we do not look at it that way. We do not look at it that way. But when we study analytical dynamics and analytical mechanics, we look at this variational formulation, and here the local statement is obtained from a global principle, principle that is applied over the whole path of the particle's travel. Therefore, it is a local statement with global implication, and that is very interesting thing to know, that this local statement has global implications. In the Lagrangian approach, we have not involved internal forces, or not solved for internal forces, we have not involved free body diagrams. Therefore, the approach is quite simple. The Lagrangian approach is quite simple, because we do not need to draw free body diagrams, we do not need to involve internal forces or solve for them. Therefore, the approach is very simple, but then in some situations we do require internal forces, and we are going to discuss that a little later, how internal forces can also be determined in this Lagrangian approach. With this, we move on to our next topic. What happens when there are external forces or non-conservative forces? Till now we were looking at mechanical systems in which the Lagrangian is written like kinetic energy minus potential energy of the system. Nowhere we have discussed what happens if there are external forces, or there are non-conservative terms, non-conservative forces which do not have an equivalent potential, which do not have a potential. Now, for such systems we have what is known as the Hamilton-Ostrogradsky principle. This is sometimes known as an extended Hamilton's principle. So, what is Hamilton-Ostrogradsky principle? Now, when we have external or non-conservative forces, we include that in the statement of now what is known as Hamilton-Ostrogradsky principle, as delta W. As you can see, delta L plus delta W, this integrated over time from T0 to T1 is equal to 0. This is known as Hamilton-Ostogradsky principle. Here we have introduced this additional term, which is known as virtual work. This delta W is known as virtual work. We are going to discuss what is this virtual work. In a mechanical system, f dot dr, f dot product with the variation of the path, this is virtual work, where f can be a function of r dot and time in general. There is one very important thing to note. When we started, we wrote the Hamilton's principle as this. This was variation of what is known as the action integral. This was the action integral, and we talked about variation of action integral. Here we cannot pull out this delta, even though this means delta of L, delta operating on L, this has no such equivalent interpretation. It is not delta variation of a work function, it is not variation of a work function. This cannot be separated. Just like we discuss in thermodynamics, dW, here it is delta W, this is a single expression. You cannot pull out this delta. Therefore, this is not a variational statement or a variational principle. Hamilton-Ostogradsky principle is not a variational principle. We cannot write delta of some integral is equal to 0. No, it is delta L plus delta W is a composite thing. We cannot pull out, it is not variation of a scalar function. As we discussed, this is virtual work done by the forces and moments acting on the particles or bodies, and usually as we will discuss, these forces, they act on the physical coordinates. We are going to discuss this point. Now, how do we understand this virtual work? So, as I mentioned, this is not a variational principle. Let us now look at what is virtual work, how to understand virtual work. Now, for mechanical systems, we had discussed this visualization of path variation of a system. Let us say this is the physical coordinate plane, or it could be the generalized coordinate plane as well. Here I have written out the physical coordinates. The brown path indicated by r star is the optimal path or the minimizing path, which minimizes the action of the system from T0 to T1. Therefore, when I perturb this path, there cannot be any perturbation at the starting and ending point. These points we have discussed before. At any intermediate time t, we have discussed the variation operator delta operating on the path delta r, and that is equal to epsilon times eta. Epsilon is a small quantity and eta is any function such that eta at T0 is equals to eta at T1 is equals to 0, because we do not have any variation at the starting and ending times, because we know the system, we know the coordinates of the system at these two time instants. Variation can occur between these two time instants. Now, when I freeze time, suppose I am looking at a time instant t, there are forces acting on the system, they are also frozen, because forces can in general be function of time. Of course, they can also be function of coordinates. At this point on the optimal path, let us say, there is a certain value of force, the force vector is now frozen because time is frozen, therefore, the force vector is also frozen. Over this, I am now giving a virtual displacement which is equal to epsilon times eta, which is the variation, this is called the variation. Therefore, the forces will do some work, there is a displacement, therefore, there will be some work. I am just shifting the system from this coordinate to another coordinate. Therefore, these forces will do some work. This is virtual work. This is the concept of virtual work. And the difference between virtual work and real work is that virtual work takes place with time frozen. That is why it is not real work, it is virtual work. I am artificially giving some variation, and because the forces are frozen, they will do some work, of course, because of this variation, because of the displacement of the coordinates with time frozen. Therefore, some work will be done, that is called virtual work. Virtual work, therefore, delta W is F, which is acting at that time instant, frozen time instant, dot the variation at that time instant, delta R. Here remember, time is frozen, therefore, forces are frozen, and over this, if we give displacements, virtual displacements, that means they do not have a time contribution, they are orthogonal to the time axis. These virtual displacements are orthogonal to the time axis. Under such virtual displacement, whatever work will be done are known as this is known as virtual work. Now, we look at the Hamilton-Ostogradsky principle. Delta L is of course delta of a scalar function L, where L is kinetic minus potential energy of the system. Delta W cannot be decomposed that way. Delta W is F dot delta R, we have just now seen that. Now, consider the physical coordinates R as a function of the generalized coordinates. Now, when we do that, I am writing this as R as a function of the generalized coordinates and time. Therefore, variation operator operating on this physical coordinates on this function can be written like this, as a summation over the generalized coordinates, partial derivative of the physical coordinates with the generalized coordinates into the generalized coordinate variation of the generalized coordinate. This is because there is, again notice that when I take variation, there is no derivation over time. Therefore, delta W can be written as F dot this delta R I have now, this delta R I have now taken from here, F is in general a vector quantity, and I am writing it over, and it in general it acts over every physical coordinate. Therefore, this I sum over I, this is the summation, the dot product is written as a summation with elements of force. Now, I can interchange the summation and write the force and the partial derivatives of the physical coordinates with the generalized coordinates. This bracketed quantity which I have written as capital Q j, these are what are known as generalized forces. Why they are called generalized forces? We are expressing virtual work. Work must be some force dot some displacement or virtual displacement. Force dot virtual displacement, and here we find this is some quantity dot virtual generalized displacements. Therefore, this must have dimensions of corresponding force. If q happens to be a linear coordinate, a displacement coordinate, then this is force, but if qj the coordinate is an angular coordinate, remember this capital Qj must be a moment. Because this can be force or moment, capital Qj can be force or moment, therefore, these are called generalized forces. The product of generalized force and the corresponding displacement or the variational displacement, that should be, that is work, that must have dimensions of work. Therefore, I have this decomposition of delta W in terms of generalized forces times generalized virtual coordinates, the generalized coordinates with virtual with the variation of the generalized coordinates. In other words, I can write this as a dot product of the generalized force vector dot the variation of the generalized coordinates. This is the generalized force vector and the whole thing is the virtual work done by the generalized forces. So, generalized forces and generalized coordinates, they the product is work. If the generalized coordinate happens to be displacement coordinate, then q must be the corresponding capital Q, the generalized force must be a force. If delta q is an angular displacement, then capital Q must be corresponding moment. Now, we come back to the Hamilton-Ostakovsky's principle and introduce this delta W. We introduce this delta W as in terms of the generalized forces and variation of the generalized coordinates. Why? Because I will pull out this delta q. This part of the derivation we have already discussed when we did not have external forces. Therefore, I start from here. This simplification I have already done. I have thrown out the boundary terms because the variation delta q at the boundaries must be 0. All those steps have been taken care of. Finally, the first bracketed quantity comes, even we have discussed this before. The only new thing is this delta W contribution. Now, I am going to pull out delta q and say that delta q is arbitrary, variation of the generalized coordinates is arbitrary. Therefore, I must have this as the equation of motion. The new term here is the generalized force on the right hand side. The structure of the Lagrange's equation remains the same, only new thing is the generalized force. To summarize, we have looked at examples of Lagrange's equation. We have contrasted and compared the Hamilton's principle and Lagrange's equation with the Newtonian approach. Finally, we have looked at the Hamilton-Ostakovsky's principle, how to take care of external forces and non-conservative forces, forces which do not have a potential. So, with that I will conclude this lecture.